Hello everyone. Now, in the previous few videos, we've been talking about second order linear differential equations. And in particular, we have focused on homogeneous equations. That's whenever the right-hand side is equal to 0. So what we will do today is start focusing on non-homogeneous equations. So in this lecture, we'll introduce some of the basics, and in the following lecture, we'll look at a more general method called the variation of parameters. Now, before we get into it today, let's introduce some theoretical concepts, some theorems, in order to sort of set the stage for what we're going to look at. So right off the bat, let's start with a theorem. And this theorem is going to say that if y1 and y2 are solutions, so they're solutions of y double prime plus p of t y prime plus q of t y is equal to, now this doesn't have to be homogeneous. This could be inhomogeneous or non-homogeneous as well. So we can have some function g of t on the end there. Well, then if you subtract these two solutions, y1 minus y2, well, then this thing is a solution of the homogeneous equation. So of y double prime plus p of t y prime plus q of t y is equal to 0. Now, let's take a look at that for a moment. What does that really say? It says that if you have two solutions to the same inhomogeneous equation, then the only way that they can look differently or be different is if they are differing by a solution to the homogeneous equation, right? So again, difference, that's a subtraction. So what is the difference between y1 and y2? Well, the only difference is homogeneous components. And in particular, that's going to be your choices of C1 and C2. So I don't usually do a whole lot of proofs in this. But I want to do this proof because this one is very easy and very informative to see what happens. Remember I introduced that notation L of y in some of the previous videos? Let's use that again. And remember we said L represents this entire left-hand side of this differential equation. So that's all that this is denoting. It's saying put y1 minus y2 into the differential equation. Well, by the linearity of this, so the principle of superposition tells us that we can distribute this over the difference, right? That just comes from the fact that this is a linear equation in y and all of its derivatives. But then this gives us the differential equation. This is this piece right here. And we know that y1 is a solution to the inhomogeneous equation. So this gives us g. But same thing, y2 is also a solution to the inhomogeneous equation. And that gives us g as well, which gives us 0. Which tells us that the differential equation evaluated at y1 minus y2 is equal to 0. That tells us that we have a solution. Remember, the goal with this L of y notation was sort of abstract things from a function of functions. And again, we're looking for roots, right? This is the common thing that we do with functions. We always ask ourselves, where are these things equal to 0? We're doing the same thing here with our differential equation. So that's our proof, right? It's 3 lines. Very, very easy, but in my opinion, very informative as well. Okay, so this sets the stage for the next theoretical result, the next theorem that we're going to look at here. And this one just builds on this right here. So what we have, again, the difference between any two solutions to an inhomogeneous or non-homogeneous equation is going to be a solution to the homogeneous equation. This theorem actually tells us exactly what those solutions look like. So the general solution of L of y equal to g of t, so an inhomogeneous equation, can be written, as, let's write this, y of t is equal to c1 y1 of t plus c2 y2 of t plus, I'm going to call it capital Y of t, where, well, you know what y1 and y2 are. So where y1 and y2 are a fundamental set of solutions. So a fundamental set of solutions. Now, we know that that's code for using the Wronskian, right? We know that that means that when you put these things into the Wronskian, they're not equal to 0 at some point, at some t naught, right? That's what it means to be a fundamental set of solutions. We remember that to be a fundamental set of solutions means that you can solve initial value problems with them, right? That's the key here. Of course, this is to the homogeneous problem. That's the only way that we talk about these fundamental sets of solutions. Of course, C1 and C2 can be any real numbers you want them to be. And Y is a specific solution. So capital Y is a specific solution, sometimes a particular solution. Solution of Ly equal to G. So the inhomogeneous equation. Now take a look at this, right? So if we combine both of these, we can really see what I was trying to emphasize with the first theorem, because what this is telling you is that solutions to your inhomogeneous equation are going to be the homogeneous part plus the same specific part. This piece doesn't change ever. The only thing that changes is you can turn the dials and change C1 and C2. That's the only way that you and I could get different solutions to this differential equation. Maybe I use C1 and C2 equal to 1, both of them. You use both of them equal to -1. Well, if we look at our solutions and we subtract them, the only thing that's going to come out is going to be solutions to the homogeneous equation, right? That's the principle of superposition at work for us. That's what that theorem is saying, right? This theorem is building on it, and it's giving us a more specific representation of our solution. Now, of course, we have to be careful here because this is a theorem. It's abstract. It doesn't give us a roadmap. So for the rest of this lecture, I would like to focus on the roadmap. I want to show you how we can actually solve these equations and find that specific solution to these differential equations, right? We spent a lot of time talking about the homogeneous solutions. So in some cases, we can find them. Now let's start talking about finding that specific solution. And here's what we'll do. Let's look at an example. So I'm going to lead by example through all of this. Let's say y double prime minus 3y prime and then minus 4y is equal to 3e to the 2t. Okay, so the first thing that we note here is that the homogeneous solution, so homogeneous solution. This is how we should always start these problems. Identify maybe the easiest part of this. Well, the homogeneous solution is obtained by just finding the characteristic equation. That's going to be r squared minus 3r minus 4, which in our case, that thing has roots given by -1 and +4. So we get y sub h is representing homogeneous, is equal to c1 e to the minus t plus c2 e to the 4t. Okay, so I got the easy part out of the way, right? The part that we already knew how to do, but that's still important because think about what we have from this theorem. The solution to this thing is going to be the homogeneous part, check, plus the specific part. So the question is, how do you find the specific part? And in this case, we're going to do a little bit of guessing. So basically, what we want is we want to put a function in here that sets us equal to e to the 2t. Now, exponential functions have a reproducing property, right? Every single time I take a derivative of them, I get exactly the same function back. It might just have a different constant in front of it. So that means that if I put in an exponential function into my L, right, the left-hand side of this equation, I would get a multiple of that exponential function minus 3 times a multiple of the exponential function again, minus 4 times the exponential function. So you wrap all that together, and I get an exponential function, right? So L of an exponential function is, again, an exponential function in this case. Well, if I'm going to get an exponential function out of this, then I want to be able to get e to the 2t out of it so that I can set these two things equal to each other. So here's what I'm going to do. I am going to search for a specific solution that has this exponential part because I know that I'm going to get it back out. But what I need to do, I need to figure out what multiple of that function is going to work in this equation to give me a solution, to give me that specific solution. So the first thing I want to do is compute some derivatives. So 2a e to the 2t, and similarly, y double prime of t is equal to 4a e to the 2t. Now that I have identified what these derivatives are, we can go ahead and toss them into the differential equation. So let's say, put into the differential equation, dE. Well, in this case, I get 4a e to the 2t. And then minus 3 times y prime, that's minus 6a e to the 2t. Minus 4a e to the 2t. And again, that's equal to 3 e to the 2t. Now look at how lovely this is, right? Because everybody's got an e to the 2t in there. I can get rid of it. That leaves me with a very, very simple algebra problem. 4a minus 6a minus 4a is equal to 3. Right? After getting rid of all the exponentials, I'm left with a beautiful little algebra problem. And so 4a's are going to cancel, and this is going to give me a is equal to minus 1/2. And so there it is, right? Now I have identified the specific solution. And so therefore, the general solution, is, well, based on the theorem that's right here, y of t is c1 e to the minus t plus c2 e to the 4t, that's the homogeneous part, plus the specific part minus 1/2 e to the 2t. So there it is, written in exactly the same form as we just saw from this theorem. So we had to do a little bit of guessing and checking, and that's going to be the sort of theme of what we're looking at here for the duration of this lecture. But nonetheless, let's keep rolling with it. Let's look at another example. So here's what I want to do. For the duration of my examples, I'm always going to use the same left-hand side. That means that we don't have to recompute the homogeneous equation every single time. This will allow us to just focus on the inhomogeneous part without, getting too bogged down in anything. So basically, all that I did here is I took my equation from the previous example, changed the function g on the right-hand side. In this case, I get 2 sine of t. Now, the first thing that you might be tempted to do is immediately sort of imprint the idea from the previous slide, or from the previous example here, onto this example. So you said, okay, well, e to the 2t was hanging out on the back here. Okay, sine is hanging out on the back here. So why don't I try capital Y of t is equal to some constant a times sine of t. Well, if I take 2 derivatives of that thing, then I get a minus 2, so minus a sine of t, pardon me, and then minus 3 times the derivative, so minus 3a cos of t, and then minus 4a sine of t, and that thing is equal to 2 sine of t. Well, let's take a look at this. I have minus 5a sine of t. So that's going to give me, so in one case here, let's actually write this down so it's clear. So this gives me, with everything underlined with this, gives me a is equal to, so in this case, minus 2 over 5. But unfortunately, that doesn't solve everything for me, because I still have a cosine term that's left unaccounted for, and that one gives me a is equal to 0. But now I have two values of a. That doesn't make any sense, right? I can't have a is equal to 0 and a is equal to minus 2/5 at exactly the same time. So this is no good for me. Now, we can see where the issue arose, though, right? The issue came from the fact that when I took a derivative of sine, I got a cosine. I didn't always have the same function. I don't have that replicating property that exponentials do. But I do have a nice property of sine and cosine, and that is when I take derivatives of both of those things, I get the other one back, right? Sine goes into cosine, cosine goes into minus sine. So let's try instead. Let's go y of t is equal to a sine of t plus b cos of t. Now, what this really tells me is that when I take derivatives of this thing, I get a sort of closure. I get just the same functions back again. So here I get a cos of t. Okay, that's okay. We've already accounted for cosine, so we're not introducing a new function. And minus b sine of t. That's good again. I'm not introducing a new function. I had that already. Similarly, taking a second derivative here, I get minus a sine of t. Again, didn't introduce anything. And then minus b cos of t. Again, didn't introduce anything. Now what you can see is I have two functions that are coming up here. And I have two unknowns, a and b. That's different than what I had in the previous case. Because in the previous case, I had two functions, but only one parameter or one constant, a, that I could tune to make this thing work. So in this case, you can take these things and put them into the differential equation. So all you're going to do is put in y double prime, and then you're going to put in minus 3y prime, and then minus 4y. I'm gonna jump ahead a little bit here, and I'm gonna show you what happens because it's just a mess. It'll take up a lot of the board. But we can say put into the differential equation. Okay, well, what happens when you collect all of the signs, you get minus a plus 3b and then minus 4a times sine of t. And then similarly, you get plus and then minus b minus 3a and minus 4b times cos of t. So that's what happens when you put y double prime, y prime, and y into the left-hand side of the differential equation. You never change the right-hand side. You have 2 sine of t now. And so now what you get is you get two linear equations. So the first one is, if you simplify this back nicely, this gives you minus 5a plus 3b is equal to 2, right? Because I have this many signs on the left, I have 2 signs on the right. Similarly, you simplify this up a little bit, you get minus 3a minus 5b is equal to 0 because there's this many cosines on the left, there are no cosines on the right. So this is sort of similar to what you would do when you're doing partial fractions, maybe when you're doing some integration problems in calculus class. But now, you've got a linear algebra problem, right? 2 unknowns, 2 equations, it's linear. You can easily solve this. You can find that a is equal to minus 5 over 17. And b is equal to 3 over 17. And now what I've done is I've identified my particular solution to this thing. And so now I can write down the general solution. So the general solution here, remember, it's the homogeneous part. We've already found that. So that's c1 e to the minus t plus c2 e to the 4t. And then plus the particular or the specific part coming from this theorem right here. So minus 5 over 17. And then sine of t plus 3 over 17 cosine of t. So I'm just putting in those numbers that I found right here, a and b. That gives me my specific part of this solution. Let's keep rolling. Let's do another example. So in this case, I want to look at, say, same left-hand side, pardon me, minus 3y prime minus 4y. So I don't have to worry about the homogeneous solution, right? It's all sitting there. But I want to set this equal to a polynomial. So let's say 4t squared minus 1. Okay, well, again, we have to sort of think about the self-replicating properties that polynomials might have that might be able to help us here. What we know is that when you take derivatives of polynomials, you get polynomials back. They just have a lower order. So if I took t squared, for example, I know that the derivative of that is 2t, and then the derivative of that again is just 2. So one possibility would be to use something like a times t squared. So you'd say y of t is a times t squared. Now, if you do that, you're going to get the same issue that we saw with the sine and the cosine from the previous example, though. There's just too many things to match with not enough free variables, in this case, a. What you can do, though, is if you augment this, bt plus c, so you use a proper general quadratic polynomial. The reason I wanted to choose quadratic is because this is quadratic right here. Then what I have is I can match for a, b, and c in order to solve this thing equal to 4t squared minus 1. So let's take a look at it. Let's put it into the differential equation. So put into the dE. Well, in this case, so the second derivative of this thing is 2a. And then minus 3 times the first derivative is 2a plus b. 2at, pardon me. And then the original thing is at squared plus bt plus c is equal to, let's put it down here so we don't spill over too much, 4t squared minus 1. Now you can see that you have enough variables to do all of the matching, right? You're going to take the pieces that are in front of the t squared, so in this case it's only minus 4a, and you're going to match it with the t squared on this side. Similarly, you're going to take all of the t terms, so bt, minus 4bt, and minus 6at. You're going to set that equal to 0 because there's no t's on this side. Then the last thing is to collect all the constants, 2a, minus 3b, minus 4c, and you're going to set that equal to minus 1. So again, it's just a matching problem, but I want you to really pay attention to the form, right? The form here is that you have to get the right polynomial, and you have to have enough free variables that you can do all of the matching when you try to set this equal to the right-hand side. All right, I'm not going to finish that example. I'm going to leave that for you to work out on your own. Let's do another example here before we sort of burn ourselves out on this. Let's do y double prime minus 3y prime minus 4y. So again, the same left-hand side, so I don't have to change anything. And let's say this is equal to minus 8 e to the t cos of 2t. So again, we need to think about self-replicating functions, we've already seen the case of sines and cosines. You have to include both of them into this thing. Now, multiplying them by an e to the t is not going to really matter either, right? So multiplying or taking the derivative of e to the t cos of 2t, well, that's just going to be e to the t's and cos of 2t's along with e to the t's and sine of 2t's. So in this case, if you wanted to make this work, here's what you should do. You should try capital Y of t is equal to a e to the t sine of 2t. You have to be very, very careful. You do need sine of 2t, not just sine of t. You won't be able to set them equal to each other otherwise. So that's a piece that you have to be conscious of. B e to the t cos of 2t. Again, it needs to be 2 in there for this to work. Now, if you do this, I'm going to leave this for you to work on your own, but the solution here is that a is equal to 2 over 13 and b is equal to 10 over 13. So it's incredible. It's tedious, right? Because we're going to have to do some product rules when you're taking derivatives. But I want to leave this for you as an exercise. You've got the solution right here. Make sure that you can actually arrive at that solution so that you really understand what's going on. So take both of these examples, try and work through them, and see, how effectively you can apply this method as practice. Okay, let's try something else. I'm going to keep scaling up the problem. Let's do y double prime minus 3y prime minus 4y. So again, same left-hand side. And I'm going to set it equal to a bunch of the things that we've already done, but I want to add them all up. 3 e to the 2t, and then plus 2 sine of t, and then minus 8 e to the t cos of 2t. I can do that, right? That's one big complicated function. But the way that you're going to approach this is basically just evoke the previous examples. So what you're going to do is you're going to divide into 3 problems. And you're going to solve each one of those 3 problems. Then you're just going to add everything together. Remember, this is a linear equation, so I can add up solutions. So the first one, y double prime minus 3y prime minus 4y is equal to 3 e to the 2t. You get a solution here. So in this case, y1 of t is equal to minus 1/2 e to the 2t, right? That's the first example that we did. So we've got that already. Then y double prime minus 3y prime minus 4y. We're going to have that burned into our brain by the end of this. And then 2 sine of t. Well, we'll call that capital Y2 of t. We already solved for that as well. That's minus 5 over 17 sine of t. And then plus 3 over 17 cos of t. And it's getting tedious, but it's not too bad. Y double prime minus 3y prime minus 4y is equal to, well, the last one, minus 8 e to the t cos of 2t, which, if you completed the previous example, or you could just look at my answer right here, this gives us another solution. Let's call it capital Y3 of t, and this is going to be 2/13 e to the t sine of 2t, and then plus 10/13 e to the t cos of 2t. And then what you can get, you get a specific solution. Well, you get a specific solution which is y of t, which is equal to y1 plus y2 plus y3. Now, why does that work? Again, it comes from the linearity of this differential equation. when I put in, and when I take, say, L of y here, then that's L of y1 plus L of y2 plus L of y3, right? I'm using that abstract notation for the left-hand side of the differential equation, L of y. But we know that L of y1 is equal to 3e to the 2t. L of y2 is equal to 2 sine t. And L of y3 is equal to minus 8e to the t cos of t. So it's tedious, but it's not bad, right? I can give you one problem, for example, this one right here, that forces you to really do 3 problems all at once, right? That's what we're seeing, all of these sort of examples rolled up into one big mega problem. Okay, so here we are. You're thinking, Jason, I've got the hang of this. I can do this. I see no issues. And I say, that's great. That's what I want, right? I want you to really understand this. And I want you to be able to do this in your sleep. So then what I do is I give you this problem. I throw you a bit of a curveball. Y double prime minus 3y prime minus 4y. And this is equal to 2e to the minus t. Now the first thing that goes through your mind, you say, Jason, that's no issue for me. I know how to do this, right? This is just like the first example we did. I'm going to use y of t is equal to e to the at. Let's say y of t is equal to a e to the minus t. Now maybe you're following along and you see the issue, because that is a solution to the homogeneous equation. So let's highlight that. This is a solution to a homogeneous equation. For all values of a. So every time you put that thing into the differential equation, so L of y, you get 0. You can never get 2e to the minus t. You've got a problem here, right? So how do we overcome this? Well, you do the same thing that we did in the previous video. You can perform a reduction of order. So if you want to, you can put a v of t in front of this. I'm going to ruin the surprise. In fact, what you want to do is you want to sort of treat this like a repeated root of your characteristic equation. You're going to go a t e to the minus t. So you throw a t in front of that the same way that you would if you had a double root to your characteristic equation, just like we looked at with the reduction of order technique in the previous video. So in this case, I get y prime is equal to a e to the minus t minus a t e to the minus t. Similarly, y double prime is equal to, so minus a e to the minus t. And then I get another one coming from taking this derivative. So I get 2 of them right here. And then I get plus a t e to the minus t. Now if I put these things into the differential equation, so let's say put into the differential equation, and I collect up all my terms, well, what you're going to get, you get minus 2a minus 3a e to the minus t. Remember, there's 2 different functions now, and you might be getting a little worried. You might be saying, Jason, well, if I have 2 functions, this is kind of like cosine and sine. I kind of feel like maybe we should have had a b in here somewhere. But watch what happens. If you collect all the terms in front of the t e to the minus t, what you actually get is a plus 3a minus 4a t e to the minus t. And this is equal to 2e to the minus t. Now, why is that a good thing? Because this is 0. That comes from the fact that e to the minus t was a solution to the homogeneous equation. And now I love it, right? This is nice and easy. This gives me, if I knock off my common factors right here, I get minus 5a is equal to 2, which gives me a is equal to -2/5. And therefore, capital Y of t is equal to -2/5 t e to the minus t. So we just kind of treat it like a repeated root. Similarly, if you had a double root here and you had the same function show up, you're just going to put another power on the t. So you're going to go to t squared instead, and it'll work out. I can promise you. Try it out. Take one of those repeated root problems from the previous lecture, and then put a g on the back of it that is exactly the same function as the repeated roots. Then what you'll find is that you can just put at squared e to the minus what, or e to the whatever that root is, and you can make that work. And it'll be exactly like this. I can promise you that. So what we saw in this lecture is ways to solve non-homogeneous equations. But I will emphasize that it's slightly limited. And it's limited because it only works for certain functions on the right-hand side. Functions that have desirable properties like exponential functions. They differentiate back into themselves. Polynomials, they also differentiate back into themselves. Sines and cosines, they swap. So they have this sort of closure of derivatives. They differentiate back into themselves. There's not too many other functions that have these really nice properties, especially ones that we work with on a daily basis. You could use, say, the hyperbolic sine and cosine functions. They also have a similar closure property to sine and cosine. But beyond that, things start getting a little stickier. And so clearly, this is a limited method. It's nice. It's relatively easy. It reduces everything to an algebra problem. Hardly any calculus that needs to be done here. But it's limited. It only works for so many equations. So what we're going to do in the next video, we're going to come back with a more general method that allows us to solve these things equal to anything on the right-hand side. But that comes with the cost of being much harder to implement. So I'll see you in the next video when we talk about variation of parameters.